In this video, we will dive into linear regression, one of the foundational algorithms in machine learning. Linear regression helps us understand and model the relationship between variables. By analyzing these relationships, we can make predictions about the dependent variable based on the independent variables. Linear regression is a method for modeling the relationship between a dependent variable, often called the target variable, and one or more independent variables, known as features or predictors. The model assumes that this relationship is linear, meaning it can be represented by a straight line. Now, let's discuss the two main types of linear regression. The first is simple linear regression, which models the relationship between a single independent variable and the dependent variable. The equation for simple linear regression is y equals mx plus c, where m is the slope and c is the y-intercept. The second type is multiple linear regression. It models the relationship between a dependent variable and multiple independent variables. The equation is y equals b0 plus b1 times x1 plus b2 times x2. And so on. Let's start by visualizing a simple linear regression example. Imagine we're trying to predict the exam scores of students based on the number of hours they study. For example, if a student studies for at least 3 hours, they will score around 40 marks. We have collected the data points for different study hours and their corresponding scores. We now plot these points on a graph, with each blue dot representing the student's score for the corresponding study hours dot and a yellow dot represents the predicted score by the model, on the left. You can see the data in tabular form, and on the right, the scatter plot of these points. Now, we use linear regression to draw the line of best fit. This line represents the relationship between study hours and exam scores. The equation of the line is y equals 10x plus 10. This means that for every additional hour of study, the predicted exam score increases by 10 marks. The intercept of 40 indicates that if a student studies for 3 hours, the model predicts they will score 40 marks. But how do we know how well this line fits the data? We look at residuals, which are the vertical distances between the actual data points and the predicted values on a line showed by red dashed line. Residuals show how much error exists for each prediction. We calculate residuals using metrics like mean squared error, MSE, mean absolute error, MAA, and R squared. MSE gives the average of squared residuals. MAA measures the average absolute error. And R squared shows how much of the variance in the data is explained by the model. And that's how simple linear regression works. The line of best fit shows the predicted relationship between study hours and exam scores, while the residuals indicate the accuracy of our model. This method is very useful for identifying trends and making predictions. But it works best when the relationship between the variables is linear. Let's begin by visualizing a 3D multiple linear regression example. Here, we are predicting exam scores based on two variables: study hours and sleep hours. The data table on the left shows the study hours, sleep hours, and the corresponding actual and predicted exam scores. Notice how the predicted scores differ slightly from the actual scores. On the right, we create a 3D graph with 3 axes representing study hours, sleep hours, and exam scores. The green dots represent the predicted scores based on the model. The yellow plane shows the actual scores based on the equation. This 3D visualization helps us see the relationship between these variables more clearly. The green dots on the graph represent the predicted scores by the model for the given study hours and sleep hours. We can see how these points are scattered in the 3D space. Now, we add the plane, which represents the actual score. This plane is generated using the equation Z equals 10 plus 5 times the study hours plus 3 times the sleep hours. Here, 10 is the base score everyone gets. Each hour of study adds 5 points, and each hour of sleep adds 3 points. This shows the combined effect of these two factors. To evaluate the model's accuracy, we use residuals, which are the vertical distances between the actual scores and the predicted plane. These distances are shown as red dashed lines. Residuals are the gaps between the predicted and actual values. These red lines show how far the predictions are from reality, helping us understand the model's accuracy. And that's how multiple linear regression works in 3D. It helps us understand how study and sleep hours work together to predict scores. Residuals help us understand the prediction errors and improve the model's accuracy. This method is incredibly useful for identifying trends and making predictions when there are multiple factors involved. However, it works best when the relationship between the variables is linear and the assumptions of the model are met. The first assumption of linear regression is linearity. This means that the dependent variable has a linear relationship with the independent variables. The second assumption is that residuals should follow a normal distribution. This ensures the errors are symmetrically distributed. The third assumption is homoscedasticity. This means that the variance of residuals remains constant across predictions. The fourth assumption is no multicollinearity. Independent variables should not be highly correlated with each other. The fifth assumption is the independence of residuals. Residuals should not follow a predictable pattern. Linear regression is widely used in various domains, such as predicting housing prices, modeling stock market trends, estimating sales revenue, and understanding the effect of advertising on sales. Linear regression works best when the relationship between variables is linear, the target is continuous, and assumptions like normality of residuals and no multicollinearity hold true. However, Linear regression is unsuitable for nonlinear relationships, categorical targets, or datasets with significant outliers. Linear regression is a simple yet powerful technique for modeling relationships between variables. Let's summarize its key concepts and applications. Let's go over these key points one by one. Linear regression predicts continuous outcomes, such as the price of a house or temperature. It assumes a linear relationship between input and output variables, meaning the relationship is best represented by a straight line. The equation for linear regression is y equals mx plus b, where m is the slope and b is the intercept. The model is optimized using techniques like least squares, which minimizes the sum of squared residuals. The performance of the model is evaluated using metrics like R-squared, which tells us how well the model explains the data, and mean squared error, which measures how far off the predictions are from the actual values. Linear regression works well when assumptions like linearity, independence, homoscedasticity, and normality are met. It can be extended to multiple variables in the form of multiple linear regression, allowing it to capture more complex relationships. However, it is sensitive to issues like outliers, multicollinearity, and overfitting, which can degrade its performance. Finally, linear regression is widely used in applications like forecasting, trend analysis, and predictive modeling. By mastering linear regression, you gain a strong foundation in predictive modeling and statistical analysis. Always remember to validate assumptions, interpret coefficients wisely, and ensure your data aligns with the model's requirements. If you liked this video, don't forget to give it a thumbs up, like, subscribe, comment, and share. Thank you for watching, and I'll see you in the next one.